Unlike kind of the perspective that everyone else is given, I'm going to go back to my experience learning GD&T. So what I'm going to talk about today is I'm going to talk about how I first started getting into GD&T as a noob design engineer. I'm going to go through a few basic things, my journey, and why did I decide to focus on GD&T, why ignorance of GD&T is really not an option in mechanical engineering, and key training concepts that we can use for our entry-level workforce. So first, a little bit about me. I graduated from Clarkson University, which is right on the northern border of Canada with New York. It's in New York. It's kind of like, Canada light, kind of like you are over here. Pretty cold in the winter. I decided to move down to South Carolina, got my first job as a design engineer for KS Gleitlager. They're a bearing manufacturer. They actually have a facility up here in Auburn Hills as well. This is where I started learning some of my GD&T. I then moved on to BMW. I was a product launch engineer for the X5 line on the F15 model. I did door analysis. And from there, I got a job with one of BMW's suppliers, ZF Transmissions, and this is where I spent the majority of my career. I was a design engineer for the 9HP line. Here's where I took a lot of the design and GD&T knowledge and really got to apply it. If I hadn't learned it early on, I don't know if I would have been anywhere near as how I was in this position. And while I was at ZF, I started an online training company called Pareto Learning. And Pareto Learning's goal is simply to teach engineers, machinists, and students early on some simple key concepts of GD&T and Blueprint reading to make sure that they have the necessary skills to enter the workforce properly. So I'm going to first start talking about my journey. Why did I focus on GD&T? And this is a nice little motivational poster. It says, "Cluelessness, there are no stupid questions, but there are a lot of inquisitive idiots." And you can find these posters. They're very tongue-in-cheek at despair.com. They're kind of too true in some ways. But when I first started out, I was a bit of an inquisitive idiot. I graduated with a bachelor's of mechanical engineering from a very good school, and they did teach me a lot. I'm not trying to knock them at all. I really learned a lot to prepare myself for this. Here's what I learned in college. I learned probably like the most of you. I learned CAD, I learned statics, dynamics, mechanics, all that, and FEA analysis, something, fairly advanced. But while I learned this, there were a few things that I was missing as a professional design engineer. I didn't have any proper blueprint training. I've never worked with 2D drawings when I graduated. I also didn't have any really good tolerance analysis experience when I started out. I didn't even really know how parts were made, how things were machined, how everything actually worked. And GD&T, of course, I was missing. I didn't have any GD&T experience because I didn't have any blueprint reading. It was kind of odd that I didn't have this because as soon as I got thrown into the design engineering role, I realized really quickly that without some of the stuff over here, you really can't do much with this over here. You can do a lot. There's good skills that you can still have. But a lot of this very basic stuff is very much needed, especially when you're working for a lower supplier like a tier 2, tier 3 supplier. It was almost like I was training to be an author, and I learned story structure and character development, but I didn't really learn how to read or even learn what a book was. So I learned how a lot of you did, learning through osmosis. As you go through, just like learning to read, you see enough drawings, you begin to pick things up. I started looking at some of the customer prints, seeing the GD&T there, not really getting what it was. I thought it was these little tweaks here and there that the manufacturing guys would just have to worry about it. I was the design, all I had was my design booklet, I had my standards, and that's all I had to go off of. But as I got more into the experience, I also learned how parts were machined and how they were inspected, just like many of you did. Enter GD&T into my world. And when I refer to GD&T, I'm referring to the entire architecture of the standard, not just the 14 symbols we all know and love. I'm talking about the entire ASME 14.5, everything from dimensioning to inch metric, all of that. So one day I had a mechanic come out to me and said, hey, we need a fixture, and I've got a handwritten drawing. Can you draw this up in CAD? This is what he gave me. He said, can you just draw this up in CAD? And like Mark and Jim and everyone else mentioned before, this is a very ambiguous drawing. I said, oh, well, I got all my dimensions on there. Everything's good. I'm pretty much all set. And I drew it up in CAD, just like I was trained to do, and I took it out to a senior CNC operator who was one of my mentors, taught me a lot about machining. And he explained to me how, he's like, well, how are your holes lined up? How's the outside of the part related to the inside of the part? How's everything else set up? And I said, I don't know, just, that's what it is. That's how it is. And he said, your part could probably end up like this. Is that okay? Well, no, it's got to be centered. Well, how much centered? And just like Mark brought up, it's not important to me. I don't care. Well, then put 25 millimeters on the print if you want. I had to learn that. And so that kind of set off a light bulb in my head that there's something I'm missing. There's something I didn't get when I learned a coordinate dimensioned type of designing when I was growing up. And he helped me refine the drawing and fix it and, get it a little bit better. I think this is what it looked like. I'm really not sure. It was about 10 years ago. So what I want to go over is how we need to be rethinking how we're teaching design kind of from the bottom up. I mean, we do a lot of CAD modeling, but we should be at least instilling a few fundamental concepts that come from GD&T into our world. The one everyone understands is size. Everyone puts sizes on their drawing. They usually don't miss a size dimension. It's tough to do. Then we have form. Form is the shape or how the part actually looks in free space. And form is controlled by your size due to rule number 1, as we learned earlier. Then we have our relatable dimensions, our relatable types of features, which is location and orientation. These are big ones that I was completely missing. I would put an angular dimension on something, plus or minus so-and-so degrees to give it an angle. But I was never quite trained that these 4 fundamentals are what truly make up a part design. And this is how we should be teaching this, and this is what we should be teaching, because this is the 4 fundamental elements of GD&T. You can't have any of the 14 main symbols without these 4 core elements. Every symbol is either a combination or a specific form of them. So this gave me a different way of thinking and really helped me accelerate my career as I went through. My original thinking about GD&T is it's just a whole hodgepodge of symbols. They're just out there. There's no consistency. They're little tweaks that you add to a part. But it wasn't until I looked at it as a whole powerful set of tools that we can use. Little by little, I realized that you're now able to give a specification of what is functionally important without tightening size dimensions necessarily. You can have a larger circular tolerance zone versus square ones. I'm sure the 57% numbers come up earlier today at some point with the circular dimension. You can also have variable geometric tolerances based on the functional envelope of the features, improving the manufacturability and your ability to both specify a functional requirement in design and then carry it out in manufacturing, but then also, as Jim was pointing out, add functional gauging to your part when you're using the MMC. And finally, it gave me a core reference system that is unambiguous for design, production, and quality. It carries along. Everyone can understand the core datum reference frame as it moves along if they understand GD&T, and especially when you're giving it to a supplier. You have the same datum reference frame if you use the same datum set. This organized everything in my head, and finally, instead of looking at GD&T as these little subtle tweaks, it was actually what should be the core of thinking in design engineering. You really should be focusing on this as a whole. Instead of just worrying about CAD, worry about how your parts fit. Worry about all of this stuff that links together. It's a way to learn engineering as you're going through design. Now we're going to talk about why ignorance of GD&T is not an option. And this poster says, teamwork, ensuring that your hard work can always be ruined by someone else's incompetence. In my short years as a design engineer, about 8 or 9 years, I've heard a bunch of very bad things. Some I didn't understand at the time were bad, but now that I'm a senior level ASME certified engineer, I now realize how twisted some of the things some people said were. Here's one thing. Let me measure that precision diameter with calipers, just like Mark pointed out. You know, you have something that's trying to fit in, I'll just take a pair of calipers and just measure it on there, you know. I've said that at one point, I'm sure, way back, you know, because that's what you get handed a pair of calipers or even, you know, a nice micrometer and you try to do it that way. MMC is the largest hole size. It's the maximum material condition. It's maximum, you know, it's the biggest. How many times have we heard this? I mean, it's easy to get confused, right? Just use a height gauge on the granite table to measure that flatness. That's all you got to do. This flatness call out, put it on a table, measure through it. But what are we actually measuring? Does anyone know? Parallelism. Or a bad table. That's true. Well, the position tolerance is the distance away from the true center. I had an inspector tell me this. And I said, well, kinda, it's half of it, but when you're using a diametric position tolerance, it's actually, you have to multiply your distance from the true center by 2. It's a total tolerance area. Whenever I see GD&T on the print, I just mark my price way up. Now this is an actual quote from a machine shop owner down in South Carolina. And then he spit tobacco into a cup. He doesn't want to see GD&T. He says it just complicates things and it makes it unnecessary inspections that he has to do. And if you've learned anything today, you should know that GD&T reduces costs. It lets you laser focus on what you want and not worry about what you don't want. Why use position? It just needs to be symmetric, so let's use symmetry. I mean, a lot of you have seen symmetry tolerances used. And when you really fully get into understanding how the symmetry tolerance is made, there are applications for it. But I would say 99% of them probably can be replaced with a position tolerance with the same functionality. And it's unnecessary measurement that you need to do. And then last but not least, this drawing doesn't have enough GD&T on it. What do I need to add? I get this all the time in our course forums. They show me a print, they say, hey, I've got this drawn up, you know, what else do I mean, I've got everything controlled, soft, but you know, it doesn't look, I don't have enough symbols. How do I add more symbols? Should I add some flatness here? And it's just like, if there's any one thing you remember, only what is functionally necessary, okay? It's like, ever play that game at the state fair where you roll the bowling ball and you have to get it between the 2 humps? So if you roll too light, you know, that's like not having enough tolerance and your part will fail. You lose right away. But also, if you roll it too hard, it rolls right past the thing and ends up hurting you on the other end because now you have super expensive parts that you can't sell. So it's important to have the right set of tolerances for the right situation. Poor use of GD&T affects everyone. Design, fabrication, measurement, and inspection. Just like I said, unnecessary tolerances add money to the design side. But not having enough control means your function is not fulfilled, and that's even worse. For production and fabrication, you either have deviations, which if they get approved, you just wasted your design engineer's time. And if they don't, though, now you got a big pile of scrap. But what could be even worse is if they make it to the final line. The only thing worse than having a part that's wrong a bunch of times is having a part that's wrong sporadically where you can't catch it. And now you got to go back and do a stop notice on your quality department and make sure they're not shipping to your customer. And finally, with quality and inspection, you could be rejecting good parts or the worst case scenario, shipping the customer bad parts. And I don't know if you've been at a company where this has happened, where you have shipped a customer bad parts, but the apocalypse comes down. Everyone, the plant manager, everyone is now on board, especially in the automotive industry. So the best strategy. If all else fails, remember this. It's what everyone's been telling you this whole day. GD&T is used to make sure the part functions properly. If you can remember that, and that's the only thing you remember from today, that's perfect. That's all you need. From design, you should be asking yourself, is this tolerance necessary for function? From production, is this part being created properly knowing the functional intent? Doesn't mean you have to create it exactly according to the datum reference frame, but you should keep in mind the functional intent. And finally, measurement and inspection. Is this part being measured in a way to mimic the functional operation? Am I doing this according to my proper datum reference frame? Because if you're not, then you're not measuring correctly. While GD&T can be beneficial for production or inspection methods, the primary goal of GD&T is to communicate exactly what is required for the proper function of the part. Doesn't mean there's no room for negotiation. Doesn't mean production can't step in and try to, negotiate with you, but you have to come back to function every time. When everyone understands GD&T, everyone will win. And these are just a few of the benefits. I'll kind of go through this fast since I'm sure by now you've learned, I'm preaching to the choir. You guys know you need GD&T. It's not something I'm trying to sell you on. Design makes sure that there's a functional importance for fixturing and can allow variable tolerances for production using LMC and MMC. Production is able to do machine setup based on a common reference frame or guidance and is able to do functional gauging online. And finally, the inspection department gives the functional effect of deviations is clear because they're measuring according to the same design datum reference frame. And feedback on NOK parts is clear. Root causes are more evident. Now, how to ensure our workforce is more knowledgeable? And this is one of my favorite ones. Genius is 1% inspiration and 99% perspiration, which is why engineers sometimes smell really bad. As I said, when I started out, I was overwhelmed, and mainly it's a lack of confidence. I could do a bunch of great things. I really could. I could design a nominal 3D design and analyze the stress strain of that design using FEA or other methods. But the problem is that we're missing in some areas. I'm not saying every school doesn't teach the right stuff. They are teaching the right stuff. It's just we're missing just a few small things that would greatly increase the confidence and the ability of our new engineers. I didn't know what I didn't know. No one told me I had to know this stuff. Reading a standard drawing, geometric tolerance ramifications, cost impacts of design choices, making drawings unambiguous, just like my other one before, that was completely ambiguous. Understanding capabilities or processes, and finally, how to talk the talk. And this is the one again, I'll make a fool of myself, but I learned this the hard way. If you ask someone, if you called up a machinist, and now this is for the inch crowd. I know a lot of you guys are in metric. I'm in metric too, but this is why, I'll just claim that's why I didn't know. And you say, I need a tolerance of 3/10 on that print right there. I need a 3/10 on that diameter. Are they going to come back with this, 0.3? This is tenths, right? This is in math. You have the tenths, the hundredths, and thousandths. You've learned that, right? Well, this would be 300 thousandths. And 3/10 to a machinist is actually this. It's 1,000 times different. It's just a terminology difference. But we never talk about it. We never talk about these differences in the way that we teach things and the way that it actually goes on the shop floor. We've done some analysis on blueprint reading at technical schools that offer associate's degrees versus ABET accredited engineering schools. Now, this is a study on about 100 schools, about 50 technical schools and about 50 engineering schools that we did. But we looked and saw which ones offer blueprint reading. And if there was a class that probably had it, we gave the schools the benefit of the doubt, or if they offered it in some way. And I'm just saying basic blueprint reading. Usually if they don't offer blueprint reading, there's no GD&T behind it. For the machinist degree, CAD, CAM, and CNC, associate's degrees, 92% of the 50 schools that we looked at had blueprint reading as a part of their curriculum. Now, we looked at mechanical engineering schools, and it was only 17% part of the core curriculum. So why are machinists asked to learn GD&T or learn blueprint reading, just the basics of blueprint reading, but our design engineers, our Manufacturing engineers, our quality engineers, the mechanical engineers that come are not offered this. I mean, I think there's electives, there's manufacturing directions that you can go into, and I think that's great. But drawings are still the primary form of communication in engineering. And I know that the 3D modeling is the new future. Everything's going to be just on a screen. You know that you look and you have the 3D model. But you still are going to need fundamental concepts that come from blueprint reading on that. You still need a way to view everything in a nice consolidated view. And even with 2D print reading, just basic 2D print reading, you guys know that the self-driving cars are coming out soon. And everyone sees it, everyone knows that they're going to be a self-driving car. But does that mean that if you had a daughter or son, you wouldn't have them get their license tomorrow? No, you probably would still have them go get their license because cars are going to be around, regular cars are going to be around for a long time, just like 2D prints. Once they replace them at an OEM, it'll take years before it gets down to the lower level suppliers. So we tend to focus on the key entry-level concepts, and this is what we believe in our company. Blueprint reading, drawing interpretation, engineering process, the basics of how a part is made, and GD&T, just basics of GD&T. These three concepts would give you the greatest impact in mechanical engineering. It's the missing link. Whether you go into design, manufacturing, quality, whatever, if it involves a part in some way that you are making, you're physically doing it. Unless you go into HVAC and thermo and that side, then maybe this isn't as impactful. But none of us in this room are in that category, I'm assuming. Now, we put together a list of the 5 must-know GD&T concepts. And Mark, you're welcome to disagree on these. I'd love to hear your thoughts on this too. First is, we actually started with 0. We're going to cheat a little because I wanted to add 6, and I couldn't figure out how to add 6, so I called this number 0. And it's the most important one, though. GD&T is used to establish what is needed for the part to function. If you can just remember that, function, 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 you'll do all right. Rule number 1, something that is core for mechanical engineers to know. It's size controls form. You know, other than the ISO standard where it's not a default, I've worked at 3 companies now that have used the ISO standard. All 3 slapped an E with a circle around it, which is the envelope principle, right on their prints, right in the title block. So even the ISO people love this rule. It's a great rule. The second is datum reference frame and datum relationships. You can't go anywhere without this. This is how you communicate a proper design through design, manufacturing, inspection, whether it's going to a supplier, where it's going anywhere else. This is how you relate everything back. SLOF, size, location, orientation, and form. Just like we talked about the 4 fundamental elements of GD&T. This is where everything relates back to. MMC and virtual condition. I like this one. It's a great tool. It adds manufacturability to a part without affecting your design function. It's something that, if used properly, is very helpful and can really reduce part costs. And finally, if you had to learn 2 GD&T symbols and that was it, pick profile and position. Everything else is some sort of derivative of these 2, the location and form orientation. Profile can do everything. Profile is the universal symbol. You technically could model everything with just profile, but if you have a feature of size, most likely going to see position on it. If you have some sort of surface, crazy surface, hood of a car, that type of thing, profile is the way to go, and profile can also control all the rest of your symbols. What we've done is we're creating academic partnerships to build customized curriculum lessons around the most important concepts that we feel that students should learn when they graduate in a mechanical engineering program. We've created a student version of our GD&T Basics Fundamentals course, and also are working on our mechanical drawing basics for students. These give all the students an entry-level view into the world of engineering in these key concepts that are oftentimes missing from engineering curriculums. We have a few current partners. San Diego State, we have roughly 500 students now who have gone through our GD&T Fundamentals course, an online course, through San Diego State University that are now able to add GD&T to their resume. They know the basics of GD&T. It's tough to teach every single thing about GD&T in a college curriculum, but we do the best we can to focus on the 20% that will make the 80% of the difference in their life. And also we're working with First Makerspace, which is a new innovative learning platform for 3D printing. We're going to be working with them on our Mechanical Drawing Basics course and our GD&T Basics Fundamentals course into their program, which teaches both high school students and college level students the basics of part manufacturing. Again, if anyone's interested in hearing more about academic partnerships, you can email me directly. We've got some great information for you. We're constantly trying to tweak college level curriculums to work these into them. And finally, something free for you guys, and again, a shameless plug. If you go to my website, gdntbasics.com, you can sign up for our email list and you will get a free GD&T Basics wall chart. And this covers all of the 14 symbols with some definitions, and it's a really nice thing to print out, 11 by 17, hang up in your cubicle. Before I ended up leaving ZF, I gave everyone at work one of them. They love it. And come give us a visit. We've got a very active community. Drop us a comment. We'd love to hear from you and hear more about you. So, does anyone have any questions? Yes?
Is the curriculum that you're using, are you physically going to the universities, or was it an online thing? I couldn't recall if you had said.
The curriculum is 100% online. It's actually, what we do is we first talk with the professors to get their curriculum goals, and then we customize our GD&T course around that in an online platform. So during the class, they're given the lecture, and then they go home and they use our course as homework, essentially. We have quizzes and handouts and everything built right into the online platform. Any other questions? All right, thank you guys. Appreciate it.